Our next speaker is Alexsander Carvalho Vendite from IV USP.
Good morning, everyone. My name is Alexander. I'm a master's student of Professor Kalini, and my work is about the atmospheric gas capture, especially CO2, with MOFs, which are meta-organic frameworks. So first of all, why is it relevant? I think this image speaks for itself. It's the temperature change over the decades, in average for the last 12 decades. And it is trending towards warmer, but it doesn't seem as alarming. Now, this is the temperature change of only the last 3 decades. And we can see that it is alarming, and we have to do something about it since it's growing faster and faster. One of the main causes of the global warming is the greenhouse effect. And there are many gases that contribute to this effect, but CO2 makes the most uh, part of it by 64% of the enhanced greenhouse effect. I just want to make a remark that the greenhouse effect per se is not a bad thing. It keeps us warm, which helps to live here. But the enhancement of it past the natural uh, state is the bad part. And in here we can see the growth of the CO2 concentration in the atmosphere from about 315 to 410 in 60 years. So it's a really fast growth, and even the slope here is even more dangerous because it's growing and not slowing down at all. There are many ways to capture CO2, and all these four here, they are meant to be used at the production of energy. So they are all related to capturing the CO2 from flue gas or removing it before the CO2 even gets released. And they deal with quite high pressures of CO2, at least 3%, but going way higher. Now, direct air capture is meant for situations where the CO2 is already in the atmosphere and we need to reduce it. But the problem is it's way smaller concentration. So the techniques involved are quite different. Now, if it's so harder, why should we do it at all? Uh, if we want to stabilize the concentration at 450 parts per million in this century, we would have to cut all of the emissions to only 10%. And that's completely unrealistic. Our economy could not handle such a change. So direct air capture could help remove some of the excess from the atmosphere and make this number more reasonable so that we can you have the environmental side and the economic side working together. In order to capture CO2, one really promising type of material are the metal-organic frameworks, or MOFs. They are made by a combination of metals and one organic ligand. And so there are an immense variety of possibilities, changing the metals, the organics, and even if you get the same metal and same organic ligand, you can make different structures. So really, there's an absurd amount of possibilities here. And among these, two important structures for CO2 capture is ZIF-8 and ZIF-78. In my work, I am studying ZIF-8, and Emmanuel is studying ZIF-78 from our group. And he's going to present a poster here. He's not here yet, unfortunately, but he will be at the poster session. His MOF 70, the ZIF78, was tested among many other MOFs and activated carbon, and it was found to be uh, the best one among these at CO2 uptake. And also the CO2 selectivity among different gases was the highest one. So it's a really promising material, but unfortunately, there are not many experimental data. So it's difficult to make a model and compared with nothing, especially since the MOFs are quite huge to use um, uh, good quantum methods. You have to pick fragments of it only. Now ZIF8 was uh, was studied longer, and there are a lot of experimental data available. So we can craft a model and compare this model with the data available, so that it is a good method. And it is also highly selectable and can take a lot of CO2 when considering the apolar atmospheric gases. So it is also a good material for CO2 capture. So in this work, the concept is to study the CO2 capture by ZIF8 and how does the other abundant atmospheric gases interact with it as well. There are many theoretical works of this already, but almost all of them focus on the bulk characteristics, and they do not take into account the surface ones. So our part here is to check exactly what does the surface do in this capture. There are this work by Gian, and he noticed that the pH of the surface of ZF8, the zeta potential of the surface of ZF8 at closer to neutral pH is positive. So we expect the surface to be positive, or it may be neutral, but not negative. So we choose different compositions for these terminations here, so that the charges would be around from 0 to 36. And we can test how does this change also affects the capture. In order to do these procedures, we used density functional theory, Born-Oppenheimer molecular dynamics, Monte Carlo molecular simulations, and molecular dynamic simulations, so that we can compare a lot of different procedures and see if they work well together. So the first step of simulations, we need the force fields, parameters. So we got these structures from ZIF8 and some of the gases of interest. And we did geometry relaxation on these and calculated the ChalPG charges. We noticed that the charges from the bulk parts, like these ones here closer to the inside, were pretty similar to the ones obtained by Hu. So our path was, reasonable. But he did not choose. He did not study the surface charges. So the ones on the outer parts here were checked, and we got the charges for the zinc on the surface, for the exposed nitrogen of the imidazole ring, and the proton on the imidazole ring. We also compared the geometry and the energy of the interactions of with the quantum methods and the classical methods. And with the Born-Oppenheimer molecular dynamics, we check that these structures are stable, so that the gases, they do not simply take away the zinc or something like that. So first of all, the Monte Carlo simulations were considered with rigid molecules. And in here, we can already see some quite promising results, because these first three are the number of molecules, of gas molecules, captured on the inside, captured on the surface, and interacting at all. And these first results can show us that O2 and argon, they basically do not capture at all. So they are not competitors here for the CO2 capture. And this first bar here, this black one, the capture on the inside, only CO2 have them. The water and N2, they are basically, they don't enter them off at all. So the inside of ZIF8 is a great domain for only CO2, even though on the outside, water and nitrogen are also captured. And we did just a small tweak on the temperature here, and the capture decreased significantly on the inside. So smaller temperatures are really good for the capture. Uh, Here we have the capture on the surface, considering different compositions of the outer boundary of the ZIF. And when we have here zinc, it means that the surface was built with zinc atoms, and H with protons or exposed nitrogens. Uh, so this is the number of gas molecules captured on the surface. So from that, it seems like CO2 is the winner. So he would be captured on the inside and the outside. But when we see the energy here, the water completely dominates the surface. So there's a fierce competition on the outside, and water gets the upper hand. So in the inside, we have CO2 being extremely selective, and on the outside, water uh, wins. So we would need a dehumidified media to capture only CO2 and do not have this problem here. Now, this is the capture on the inside. And in here, we can see the CO2 dominance. The other ones, especially with slightly higher charges, will not be captured at all. And interestingly, the capture of CO2 increases with higher charges only when we add more zincs. When we increase the charges by adding more protons, it doesn't help. So the presence of metals on the surface increase the capture on the inside as well by a lot, not the charge only. So these are a lot of different experimental data that other people have already gotten, and all of them are verified in our work. So oxygen and argon can only be captured at lower temperatures. So this is extremely lower than ambient temperature, and that's what we saw. It barely did not interact at all. Water is only adsorbed. So on the surface, there's a high preference for water, but it doesn't enter the ZIF-8 at all. High selectivity towards CO2 in the pores. That's also what we found among all of the tested gases. CO2 had the highest preference by far on the inside. Both capture and selectivity of CO2 increased with lower temperatures. We saw that a slight change in the temperature decreased the capture by 1/3, even close to a half. So in order to increase this potential here, lower temperatures are really important. Surface conditions are fundamental since smaller nanoparticles capture more CO2. That means smaller nanoparticles have a higher ratio of surface to volume. So in these cases, the surface is more present and the capture is enhanced. So that means the surface is really important to capture on the surface. And also, MOFs in general, not just these ones considered, they absorb water on the surface, and usually they get bad at capturing after it because the water stays in there, and since the interaction is really strong, it's the capture doesn't work well after it. So we really need to dehumidify the air before trying to capture. Then we tested the flexible case to check whether the rigid works well or not. The big problem that we had was about the set of force field parameters, since the ones that we had from early works that were done, they did this with the ring, the imidazole ring. It was completely distorted, and we had to solve this. So after many attempts, we managed to get a stable structure, and we saw that the CO2 capture increased even more than before. That means that the flexibility can really help the capture uh, of CO2 and even further than what we had before. But other than that, the other results were quite similar. So the flexibility enhances the CO2 capture, but the other results from rigid frameworks are reasonable as well. And also, nitrogen cannot do anything about the adsorption or the capture on the surface, even at really bad odds for CO2. So only 10% of CO2 and 90% of nitrogen, still made the capture on the surface completely do, done by CO2. The nitrogen could not do anything about it. So I would like to thank you all for the attention and everyone here involved.
We are all open for questions.
Alexander, it's the same question that someone from Shell did for me some months ago. Why we are using the metagram frameworks if they are not so stable at room temperature?
They are pretty stable at room temperature. They are not in the presence of water, but without it, they are stable.
But if you want to use it to capture, this is what the guy returned from me. But if you want to use it to capture CO2 in an environment, when it's humid, you have water in this environment.
Yeah, the water would need to be removed previously, especially since water is the only, considering the most abundant ones, is the only polar one. So it could be removed with not, it wouldn't be so hard to remove water. And seeing how it selects among the other apolar gases, it still stands as a good option.
Do we have?
My question is more, for example, that kind of material you can capture the carbon dioxide, and then imagine how do you release that carbon dioxide to use this like produce other kind of fuels or material.
So that slight change in temperature made a drastic reduce of the capture. So if we capture at room temperature and then heat it slightly, it will already release a lot. There's also the possibility to reduce the pressure. So both temperature swing and pressure swing could be easily used to remove the CO2 from the structure and allow it to capture more CO2 afterwards.
And I have another question. Okay. Do you know in your experiments how the carbon dioxide is linked on your material? For example, it keep like a carbon dioxide or could produce other intermediate like a carbonate or another molecule?
From our flexible framework simulations, we saw that the CO2 doesn't get bent. So we don't expect it to be changed somehow chemically. But there's a high preference for the surface termination. So the zincs on the surface aid a lot in the capture. And there is some inside which get inside because of the interaction of the high charge that the surface has, but the most part of CO2 gets on these metal atoms here.
Thank you.
Only complete this answer, Alex. We also did ab initio molecular dynamics, and we saw no chemical reactions on that. All the CO2 molecules stay intact with the geometry, electronic properties, and so on. So that's why we did Bohr-Oppenheim molecular dynamic, try to see if with the classical force field we couldn't see, but in the quantum, if there are some reaction, some breaking bonds, some rearrangement in the surface, and we saw nothing. No, what we have as experimental data in the literature that either you see reactions when you have specific conditions to take the metals off of the surface, or when you don't have this condition, reactions doesn't happen, only capture.
Last year, when I was with the group of Professor Holland Fischer in Germany, they are specialists on these MOFs, several of them, I think, a wide range of different metal frameworks, but they are encapsulating transition metal particles at a smaller size inside of those systems, and then use them to break CO2. This is, I think, the knowledge that you are developing on the metal framework, maybe you'll be successful with the capture, but maybe you can use it for also different things too. That goes beyond only try to capture it.
Yes.
Because if you can be attracted and inside of it, it could be broken. It could be something that's interesting. Because they are really testing for that too.
Yeah, for sure, especially the ones that are lacking coordination on the surface. These ones, if there's a cluster here, for example, I think they're quite likely to aid on that.
Do we have more questions? Okay, no. Let's thank the speaker again.